The CPU, or central processing unit, functions as the brain of the computer. It excels at handling complex sequential tasks that require deep logical reasoning. In contrast, the modern GPU is the muscle. It contains thousands of specialized cores designed to process massive amounts of data simultaneously. Instead of solving one complex problem, it solves thousands of smaller ones all at once. By 2026, the GPU has evolved. It is no longer just for graphics. It is a critical engine for generative AI and complex physical simulations, effectively acting as the foundational hardware for the future of computation. To understand the fundamental difference in architecture, consider how CPUs and GPUs handle tasks. The CPU is like a master brain, optimized for complex serial logic. It processes one difficult task at a time, very rapidly. Conversely, the GPU is like a massive array of muscles, containing thousands of small cores designed for parallel work. While the CPU performs one calculation at a time, the GPU performs the same operation on thousands of data points simultaneously. This parallel architecture makes the GPU essential for tasks like rendering, AI, and scientific simulation, where data can be processed in bulk. SIMD stands for Single Instruction, Multiple Data. This architectural principle is the secret behind the massive parallel processing power of a GPU. Instead of processing one pixel at a time, the GPU broadcasts a single instruction across thousands of data points simultaneously. Watch as one instruction, like adding a value, is applied to the entire grid in a single clock cycle. This efficiency is why GPUs can handle millions of complex calculations, making them ideal for rendering graphics and training modern artificial intelligence. The graphics pipeline begins with vertex processing. Here, the GPU defines geometric shapes in three-dimensional space using vertices to build the framework of every object. Next is rasterization. This step converts the mathematical vectors into a grid of discrete pixels, determining exactly which points on your screen should be lit up. Finally, fragment processing applies the finishing touches. This stage calculates color, lighting, and texture data for every pixel, transforming raw geometry into the final image you see. To process complex data, GPUs require a high-speed workspace known as video RAM, or VRAM. This is distinct from system memory, optimized specifically for massive, concurrent data access. Think of VRAM as a high-speed pantry. The GPU cores, acting like a chef, need instant access to textures and data. Without this high-bandwidth link, the processor would sit idle, waiting for information. Modern standards like GDDR7 or HBM3E provide incredible bandwidth, ensuring that textures and geometry data arrive at the cores as fast as they can be rendered. By keeping this workspace packed with the next frames and calculations, the GPU maintains peak performance, eliminating bottlenecks in the rendering pipeline. Historically, GPUs were built as a single monolithic die. While powerful, building one giant chip is extremely difficult and prone to manufacturing defects. Modern architectures have shifted to a modular chiplet design. By breaking the GPU into smaller, specialized blocks, we increase manufacturing yields and reduce costs. These chiplets are connected by a high-speed fabric, allowing us to mix and match compute and memory modules for better performance and efficiency. Modern GPUs have shifted away from rendering every single pixel raw. Instead, they use AI upscaling techniques like DLSS and FSR. The GPU renders a lower resolution frame, which is significantly more efficient for the hardware to process. Specialized hardware blocks called tensor cores analyze these frames. Using pre-trained AI models, they intelligently guess and fill in the missing pixel data. This process produces a final image that is virtually indistinguishable from a high-resolution render, but with significantly lower power consumption and much higher frame rates. At the heart of every AI model is a mathematical operation called matrix multiplication. These operations involve thousands of simultaneous calculations. Standard GPU cores process single values sequentially. Tensor cores are different. They are hardware blocks designed to compute an entire block of data at once. By accelerating these matrix operations, tensor cores allow modern GPUs to render intelligence as efficiently as they render graphics. Today, the modern GPU has transcended its traditional purpose. While it was built to render pixels, it is now the powerhouse of artificial intelligence. Remarkably, over 65% of all GPU cycles in today's data centers are dedicated to AI inference and training, rather than rendering images. The GPU excels here because it performs parallel matrix operations. It handles thousands of calculations simultaneously, transforming raw data into intelligent outcomes. The muscle of the GPU is no longer just drawing frames, it is the backbone of global intelligence. In traditional computing, the CPU and GPU reside in separate worlds with their own dedicated memory banks. Data must be copied across the bus between system RAM and VRAM, creating significant latency and overhead. Unified memory architecture changes this by providing a single shared pool of high bandwidth memory for both processors. By eliminating the need to copy data, the system achieves near instant access, massively improving efficiency for AI and real-time processing. In the modern era, the most critical metric for GPU design is no longer just raw speed, but performance per watt. To meet the demands of massive data centers while maintaining sustainability, GPUs now employ intelligent power gating. By identifying and powering down unused silicon clusters, the chip saves energy during periods of lower demand. This optimization ensures that every watt of electricity is translated directly into computational results, rather than lost as wasted heat. In modern AI superclusters, the primary bottleneck isn't the computing power itself, but the movement of data between GPU clusters. Traditional copper wiring faces significant signal latency. The industry is shifting to photonic or optical interconnects. By converting data into light pulses, we can transmit information across server racks with near zero latency. This transition allows massive GPU clusters to function as a single, unified entity, fundamentally scaling the capabilities of sovereign AI infrastructure. Heterogeneous computing is the engine of modern performance. It dynamically assigns specific tasks to the processor best suited for that job. The CPU handles complex serial logic and control instructions. The GPU excels at massive parallel math, perfect for rendering and simulation. The NPU, or neural processing unit, focuses specifically on the intense matrix multiplications required for AI tasks. By intelligently partitioning workloads, modern systems maximize performance and energy efficiency. In VR and AR, rendering a full 360-degree field of view at maximum quality is computationally expensive. Human vision works differently. We only perceive high detail at the very center of our focus, known as the fovea. Foveated rendering tracks the eye and renders only the small area where we are looking at full resolution. The surrounding periphery is rendered with significantly less detail, saving massive amounts of power without sacrificing perceived quality. In 2026, the frontier of high-end gaming has shifted. We've moved from power-hungry desktop architectures to highly efficient, low-voltage designs that fit into handheld devices under 15 watts. Optimizing for a sub-15-watt envelope requires aggressive voltage scaling. By running the silicon at lower clock speeds, we leverage the cubic relationship between voltage and power consumption. Through fine-grained power gating, these GPUs intelligently shut down inactive silicon regions, ensuring every milliwatt is directed only where it is strictly necessary. This architectural precision is what makes modern handheld gaming possible, delivering console-grade fidelity at a fraction of the power. We are entering an era where raw, general-purpose clock speed is no longer enough. We have reached the limits of shrinking transistors for general logic. Instead of trying to make a general processor do everything, we are now building dedicated hardware blocks. These blocks are hardwired for specific mathematical operations. Take matrix multiplication, the heartbeat of AI. A general processor requires thousands of instructions to compute one matrix. By creating a domain-specific architecture, or DSA, we move that math directly into the silicon logic. This allows the GPU to process entire matrices in a single clock cycle. This is why modern AI reasoning and scientific simulations perform orders of magnitude faster. We aren't just calculating harder, we are building hardware that calculates better. Modern GPUs go far beyond rendering images. They are now the engines for digital twins, which are exact virtual models of complex physical systems. By dividing physical structures into millions of small cells, the GPU computes forces, heat, and structural stress on every single point simultaneously. The GPU's parallel architecture processes these physics equations in parallel, turning static blueprints into active, predictive digital environments. These twins enable engineers to stress test infrastructure before it's built, and climate scientists to forecast complex weather patterns with unprecedented speed. The raw power of a GPU is only accessible through the software layer. Think of libraries like CUDA or ROPM as vital translators. Without these stacks, developers would have to communicate with silicon gates directly, which is practically impossible for complex tasks. The software stack takes high-level code, manages memory, and optimizes instructions, ensuring the GPU muscle performs effectively. Whether it is NVIDIA's CUDA or AMD's ROCm, these stacks are the bridge between human logic and massive parallel hardware. In the landscape of modern artificial intelligence, nations are increasingly prioritizing sovereign AI. This means moving away from a reliance on universal global cloud models. Instead, countries are building private, localized, high-end GPU clusters to develop their own context-aware artificial intelligence. This approach ensures that national data remains secure and the resulting models are custom-trained to respect local culture, language, and legal frameworks. At the heart of these facilities are massive arrays of GPUs. These provide the massive parallel compute power required to train models from scratch, independent of external service providers. For decades, Moore's law drove exponential gains in compute. Today, we face a plateau. While raw transistor density still grows, the practical performance gains for standard rendering are diminishing. Static photorealism is effectively solved. We can render near-perfect environments with ease. The new frontier is no longer just how things look, but how they think, reason, and simulate physical reality. This pivot has led to domain-specific architecture. Instead of general-purpose chips, we are integrating hardware blocks designed specifically for matrix multiplication and high-fidelity physical simulation. GPUs are evolving into agentic engines. Beyond simple graphics, they now drive autonomous AI agents that perform multi-step planning and reasoning. This shift requires high-speed unified memory architectures, allowing the GPU to store complex states and reasoning chains directly on the silicon. By integrating logic-heavy AI blocks with traditional parallel processing, the GPU transforms from a visual renderer into an autonomous reasoning coprocessor. A modern GPU is a masterpiece of silicon engineering. While it appears as a single piece of silicon, the die is actually a highly organized city of specialized processing units. At the center lies the massive grid of shader processors, the muscle of the chip, handling thousands of parallel tasks simultaneously. Surrounding the shaders, we find the peripheral logic. Memory controllers manage data flow, tensor cores accelerate AI matrix math, and the CPU interface acts as the gateway to the rest of the system. Information zips through these components at nanosecond speeds, orchestrated by complex data paths that link the general-purpose logic to the specialized AI engines. By dividing the die into these specific zones, modern GPUs achieve an incredible balance of raw graphics performance and efficient AI computation. The modern GPU has completed its evolution from a simple rendering tool into a global computation engine. It is defined by three fundamental pillars: as a massive parallel engine, a specialized math powerhouse, and now an essential AI coprocessor. Looking ahead, the frontier of GPU technology shifts focus toward extreme power efficiency, autonomous AI reasoning, and high-fidelity real-time physical simulation. As we move into this future, the GPU will remain the bedrock of sovereign AI and digital twin infrastructure, driving the next wave of technological capability.